and welcome to another college math video. In this video, we're going to take another look at the counting principle, telling us how many different ways we can do something, and then we'll also take a look at permutations. So our objectives for this video: look at vocab and concepts related to the counting principle and permutations. We've seen counting principle, but it comes up again. We're going to evaluate factorials and permutations. We're also going to look at how you can do those in the calculator. And then we'll also solve applications involving the counting principle and permutations. All right, so our notes for this video. Just a friendly reminder, because we've already seen the counting principle. Remember that the definition for counting principle: if a first experiment can be performed in m distinct ways, and a second experiment can be performed in n distinct ways, then the two experiments in that order can be performed in m times n distinct ways. And we also noted that if it was 3 experiments, it could be more than 2, 3 different things multiplying each other. So that was when the experiments were potentially completely different things. All right, our definition for permutations is any ordered arrangement of a given set. Any ordered arrangement of a given set. And the most important thing to take away from the definition of permutation is that it's an ordered arrangement. This video and the next video are very closely related, and so we'll see the distinction in the next video about when the order doesn't matter. So what's important here is that the order does matter. We care about first, second, third, fourth, however many places there are. Okay, and then here's our definition for a factorial. So permutations, if we're using every single item in the set, will be a straightforward factorial. This is how you would see it listed: n factorial. N is just going to be a number. So if it says, well, I'll give you an example in a moment, if it says a specific number. But this is what it looks like. We take that number and multiply it by that number minus 1, multiplied by that number minus 2, that number minus 3, all the way down to 3 times 2 times 1, all the way down the line. The length of this computation will vary depending on your number, but honestly, it looks a lot scarier here than it really is. An example of a factorial, 5 factorial, as the definition says, it's that number times that number minus 1, so times 4, times that number minus 2, times 3, the number minus 3, which is 2, all the way down. It's just subtract 1 and keep multiplying all the way down the line. That's what it looks like. Let's see when you would use something like that. So our first example, let's say we have 6 gymnasts on the Belarus women's Olympic team. How many different ways can they place first through 6? There's a couple different ways we can think through this. The first way would be the old way of using the counting principle, which is fine. Counting principle. With the counting principle, we said how many experiments are there, and we'll multiply all the different ways each experiment can happen. Well, there are 6 gymnasts, and we care about them placing first, second, third, fourth, fifth, and 6th. We care all the way down the line how many different ways they can place first through 6th. And then counting principle says we fill in how many different ways each thing can happen. So there are 6 gymnasts. How many different ways can someone place in first place? 6, because there are 6 different gymnasts. Okay, now first place has happened. Someone has placed. How many different ways can they place in second? Then there's only 5. Someone has placed. How many different ways can you place in third? There'll be 4. Again, you've got a first, second, and third at that point, so there's only 3 gymnasts remaining. 3 different ways to get 4th place, then 2 different ways to get 5th place, and then there'll be 1 person left for 6th place. So the counting principle looks like this. Multiply all of these numbers together, we get 720. The alternate way of doing it is to use the factorial. And we use the factorial when placing all items. I'm using the term items. In this case, these are gymnasts. All gymnasts are being placed first through last place. but it could be lots of different things. So use when placing all items. And the factorial says we take our total number, 6 factorial, 6 times 5 times 4 times 3 times 2 times 1, and we get the same thing, 720. So ultimately, using the counting principle, we were doing the factorial. So essentially, they become the same thing. The counting principle works when you have lots of different scenarios. It could be that each experiment is different, or it could be that it's the same thing. We're just placing all the different items first through whatever. So the factorial can more specifically be used when you're placing all items first through, let's note that, first through last, whatever last place would be. In this case, it's 6th, but it'll vary from question to question. Counting principle can work here, but it also works when the experiments are different or you're not necessarily using all the items. So something to keep in mind there. All right, the next thing I want to do is show you how to do these on the calculator. So there's 2 different calculators that you might be using, so I'm going to show you both of them. There's more than these 2 available, but these are the 2 most common, so this is what I'm going to go with. If you have a different type of calculator, truthfully, you'll probably be able to figure it out based on the explanations for these 2. So if you're using a TI-84 and you're wanting to do the factorial, the button that you would hit is the math button. When you hit the math button, it's going to bring up this menu right here, and it'll start out on the first one of math. You'll see the options there. You want to scroll using your right button over to the probability menu. That's what PRB means, probability. And then within that menu, you'll see quite a few different options. There's only 3 that we're going to use at all throughout this chapter, and they are all right here. There's one that we've seen thus far, it's the factorial. We will also do NPR, which is permutations in this video, and then NCR, which are combinations in the next video. So if you are typing in, you want the calculator to do your factorial instead of doing it by hand, you will just type in your number, then you'll hit the math button, then you go to probability. You can hit 4, or you can scroll down to the factorial. You'll see on the screen your number, let's say it was 6. You'll see 6 factorial, and then you hit enter. And it'll give you 720. Sometimes it's easy to do the factorial by hand, just 6 times 5 times 4. If they're bigger numbers, if you're doing 12 factorial, that's a lot to type in. So it's your call. You don't have to use the factorial button if you don't want to. But sometimes it's easier. All right, and the other thing that we'll do in the calculator, and I'll show you both things, are using NPR and NCR. So for example, you're still gonna go into the math menu, still scroll over to probability, but if you're typing in an NPR and NCR, the process is exactly the same. An example of an whoops, there we go, that's what I want. An example of an NPR could be 10, permutation 5. This is how you would type it in. You would hit 10, then hit the math button, and scroll over to probability. Then you can hit 2, which would bring up NPR. What you'll see on the calculator is 10, NPR, and then you'll type in your remaining number, which is 5, and then you hit enter. Put that in a box. You'll see that. You'll hit 5, hit enter, and it's going to do the computation for you. We will see problems like this soon. We haven't done one like it yet, but I just want you to know how to type it in on the calculator. You can reference this part of the video if you need to see how to do it in the calculator again. And the process for NCR for the next video is exactly the same. You'll have a number, C, a number, and so the process, you would just pick 3 instead of 2 for that option. So this is if you're using a TI-84. All right, if you are using a TI-30, the process is a little bit different. Let's say we're doing 6 factorial first. 6 factorial. You can see that there's a PRB button here. That's the one that you're going to choose. So what you would do first is type in 6. Then you would hit that PRB menu. Remember, just like it did in the other calculator, this means probability. And then what you'll see show up are three options. You'll see them in this order. It's going to initially underline NPR. You just use the arrow to the right to move over and choose the one that you want. So you would hit NPR, then you would hit arrow, arrow. It will then be highlighted under the exclamation mark, which is your factorial. You hit enter. What you'll see on the screen is 6 factorial, and you hit enter again for the calculator to do that computation, and then it will show you 720 as the answer, as we saw it was for the other one. And then your process for doing an NPR or an NCR is very similar. I can list it underneath. Let's say you wanted to do 10p5, you'll type 10. I guess this is a button too, probability, PRB. If we're doing NPR, it's already going to be on that option, so you'll hit enter. If you wanted NCR, then you would just scroll over one time. And then you'll hit your second number, which is 5. You will see 10 NPR5. You hit enter, and it'll give you your answer. Again, we'll see problems where that's required soon. But for now, I just want you to have seen how to do it in the calculator. And if you're using a different type of calculator, just look for this PRB somewhere. If it's a scientific, then you probably see it somewhere on the screen. If it is similar to the TI-84, then you probably are looking for a math button. Or the PRB might be above one of the keys. So just look for that menu, and then you should find PRB for probability. Okay, so let's actually look at this permutation formula. Remember that permutation formula means R objects, or in general, we haven't discussed this yet, but it means R objects selected from N objects. And let's add this as a note, in a certain order, because with permutation, the order matters. We care what was first, second, third, fourth, and so on. So there'll be a certain number of objects, and some of them are being selected. So we're placing them in order, but not all the way first through last necessarily. So NPR is kind of the simplified prior to computation notation you'll have. And this is what the formula looks like. It's N factorial, so your total number of objects, factorial, divided by N minus R, and then factorial. N total objects, R of them being selected in a certain order. Now we can do this computation by hand, or we can use the calculator. We can just type in if it was 10p5 in the calculator, and it'll do the whole thing for you. I'll show you both ways when we see an example of this. Okay, so let's say that we have the same scenario, 6 gymnasts on the Belarus women's Olympic team, but maybe we only care how many ways they can finish in first, second, and third place. So let's look at it a couple different ways. We could use the counting principle. It still works here. The counting principle says, okay, we care about first, second, and third. Counting principle says, how many experiments do you have? Multiply the number of ways each experiment can be performed, and that's your total number of ways the experiments as a whole can be completed. So there's 6 gymnasts, so there are 6 ways someone could finish in first, 5 ways then someone could finish in second because someone's already placed. Then there's 2 people that have placed, so 4 ways someone could finish in third, which gives us 120. Alternatively, we could use the formula, which is our permutation formula. There are 6 objects, and how many of them are being selected if we care about first, second, third? There are 3 objects. Again, objects has to be the general term, being selected. So we care about the order, so we know it's a permutation. There are 6, and 3 are being selected. We care about first, second, and third place. So the formula says, let's do it by hand first, 6 factorial, so this piece goes up top. I'm going to write the formula again in case it's far away. Divided by n minus r, so 6 minus 3 factorial. So 6 factorial over 3 factorial. Let's bring this down here. All right, 6 factorial on top is 6 times 5 times 4 times 3 times 2 times 1. You could do that in the calculator independently if you wanted. I'm going to show you it completely by hand here. And 3 factorial is 3 times 2 times 1. You'll notice 3 times 2 times 1 is both on the top and bottom, so they can cancel out, leaving 6 times 5 times 4, which is 120. So essentially it boils down to exactly the same thing that the counting principle has. It just is a little bit more systematic in using the formula. The third option you have, if you're using the formula, second using the formula, is just to type it in the calculator. And so you saw how to do this earlier in the video. We would type 6, we'd hit the math button or hit the probability button, scroll over so that we have NPR chosen, then hit 3, hit enter, and this will spit out 120. It's just going to do the entire computation for you. So any of the 3 ways is totally fine. In this video, counting principle will work for the problems, but in the next one for our combination, it's a little bit more complex to do it using counting principle. I'll explain how it works, but it's pretty difficult. So I would be comfortable with both. For me personally, counting principle right now feels more comfortable just because, I don't know, the formula is a little, it looks a little crazy with the factorials in there. But be comfortable using both because when we get to combinations, you're pretty much stuck using the formula. But you can see how it would work out by hand and then doing it in the calculator. And then let me just note that, again, the formula is good. The formula, your NPR formula, is good when you're using some of the items. First through something, but not last. If we went all the way through last, then the straightforward factorial would work. The good news is even if it is first through last, the formula here would work. So you can default to the formula in all cases if you'd prefer. Okay. Let's see one more type of problem. This is a permutation of duplicate items. So we have n objects where a certain number of them, n1 and n2, however many, we'll see an example, are identical. So an example of this is typically when we have words. So let's say, and a special note, that 0 factorial, you can type that in the calculator if you want to prove it, is 1. It's not 0. Otherwise, it would mess everything up. So an example we can use, I don't think I have, yeah, we can do it here. Let's say we want to know the number of ways that the word monkey can be arranged. Words have the potential for items to be identical. When we're talking about women on the Olympic team, they're definitely all different people, all 6 different people. But when we're talking about letters, there could be repetition. All right, so if we have an example with the word monkey, how many ways can the word monkey be arranged? We have 6 different letters. And in this case, they're all different. So if they are all different, then you can use counting principle. How many different ways to place the first letter, the second letter, the third letter, the fourth letter, the fifth, and the 6th letter. And it would very simply just be, I want to show you one example both ways where they're not, they're all different, and then where some of them are repeated. If they're all different, it's very simple. You can just use a standard factorial down the line. 6 times 5 times 4 times 3 times 2 times 1. We already know is 720. We saw that in an earlier example. This specific formula, and we'll see an example of it on the next page, I just want to note when it would be used. This is when you're using, using all the items, but you have repetition. So for this one in particular, we didn't have any repetition, this example, so there was nothing that we needed to divide by. There were no pieces of repetition, so they were all 0 factorial down here. We divided by 1, which still gave us 720. But if there is repetition, then we'll do a standard factorial, but then divide out where we have repetition. Okay, so let's see that example. Let's go back to this. Find the number of ways the letters in the word banana can be, bananas can be arranged. So this is the one that we care about. The first thing we need is how many different letters there are, because the formula says N1, N2, and it looks like it's really long, but it has to be long because we don't know how much repetition there is. So the first thing we need is how many items there are. That's our numerator. We have 1, 2, 3, 4, 5, 6, 7 is our N, since there are 7 letters in this word. So 7 factorial divided by, okay, where do we have repetition? We have repetition amongst the A's. There are 3 of them, so this can be our N1. And we have repetition amongst the N's. There are 2 of them. This can be our N2. You could label 3 and 2 as N1 and 2. If you flipped it, it doesn't really matter. But that's where we have repetition. And you can see that, let's say this was one iteration of putting down those letters, but here's a different one if I swap these 2 letters, N and N, but it doesn't give me a different word. So that's what we're dividing out, is the repetition. So we divide out a 3 factorial and a 2 factorial for the places we have repetition. If they were all different, like in monkey, we would just need to do the numerator, but we've got repetition in this word, we have to divide that out. Now, there's no simple one type in the calculator to get an answer like this. You can use the factorial a few different times, or you can do it by hand. I'm just going to do it by hand, but it's up to you. This is what 7 factorial looks like. Then we have 3 factorial, which is 3, 2, 1, and 2 factorial, which is 2 times 1. We've got a 3, 2, 1 and a 3, 2, 1 top and bottom. And then the 1 doesn't really do anything, so it doesn't matter. The 2, I'm going to simplify with the 4 to give me 2. This is me doing it by hand. You are more than welcome to just type 7 factorial over 3 factorial, 2 factorial, and get your answer. Leaving 7 times 6 times 5, and then times 2. This one we'll type in, 7652 gives us 420. So there are 420 different ways we can take the letters in the word bananas and rearrange them to get different iterations of the letters. If they were all different, just 7 factorial would be good because there would be no repetition. But there's a lot of places where 2 N's get flip-flopped or 2 A's or multiple A's get flip-flopped, and it's still giving you the same scenario. So that's what we're dividing out. All right, so we've seen one of each of the 3 types. Now we'll look at just general examples. There are 5 cars in the Monaco Grand Prix. How many ways are there for those cars to finish in first and second place? So we're placing some items, not all of them. We have 5 total cars. Again, you can look at this multiple ways. You can use the counting principle, which would be how many ways can we place in first and how many ways can we place in second. 5 different ways to place in first place, and then 4 to place in second. Since someone has already placed, you can imagine they've crossed the finish line, now it's just a battle for second. There'd only be 4 left, which would give you 20 different ways. Or you can use the permutation formula, which says we have 5 objects and 2 of them are being selected. We care about the order of those 2, so it's a permutation. You can plug it in the formula or do it in the calculator. 5 factorial over 5 minus 2 factorial. This is 3 factorial, 3, 2, 1. Again, 3, 2, 1 gone. We have 5 times 4, which is 20, or you could have just typed it in the calculator. Either is totally fine. Your answer is 20. I'm never asking you to do it both ways. I just want you to see it done both ways so that you know it's possible. And if you have a preference, then you're seeing the way that you would do it yourself. All right. Let's see another example. You need to create a password that fits these standards. 3 letters followed by 4 numbers. If there's no repetition, how many ways can this be done? No repetition. Now, sometimes those formulas, they only work in the majority of scenarios, but for something like this, it's really difficult to think through this problem without using the counting principle. For me personally, I'll show it to you multiple ways, but maybe you'll agree with me. Who knows? So if we use the counting principle, we know that we are creating a password that has 3 letters, very specific, followed by 4 numbers. These are all the experiments, according to counting principle. Just multiply the number of ways each experiment can be performed. No repetition is allowed, so everything has to be different. Even though sometimes in a password you can choose the same letter, these are the very specific standards put in place for this password. So the first choice for the letters, we have 26 choices. Those are all the letters. Don't worry about capital, non-capital for now, just the letters. Then, in the second choice, there's no repetition, so we would only be able to have 25 choices. And then the third selection, we have 24 choices because we've used a letter and we can't repeat. Then we go to the numbers. How many different number choices do we have? It's tempting to say 9, but 0 is a digit that you could choose. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, and 0. So there are 10 choices. After we choose our first number, one of those digits is gone, so there's only 9 options. Then 2 of the digits are gone, so there's only 8 options. 3 of the digits are gone, there's only 7 options. So multiply these straight across. Now keep in mind, these are not our selections. We're not saying 10, 9, 8, 7 is the password. That's how many choices we have in each selection. 10, 9, 8, 7. Okay. A huge number, 78,624,000. Now, truthfully, in a password choice or when you make a password, you're never given criteria this specific. 3 letters followed by 4 numbers. Truthfully, you usually have way more choices than that, and you usually don't have to have 7 characters. You can have more. So imagine just if amongst the letters we said, okay, there's a difference between capital and lowercase. This isn't about the problem. This is just passwords in general. Then we would have 26 times 2 choices. We would have, my head doesn't want to do it, 52 options, then 51, then 50 choices. This number is already 78 million, more than 78 million, which is a crazy scenario. Truthfully, you have so many more choices. These numbers are much larger, which means in general, when you make a password, you have billions of options. How hackers can get into those things is it's just crazy, but they have computers that can run through things. It just makes you think about why wouldn't we all choose very intricate, detailed passwords that would be hard to figure out? Who knows? All right, so this is using counting principle. If we use the permutation formula, we're using 2 different permutation formulas, or we're using it twice, because we're making 2 selections. We've got 26 choices, and we are selecting 3 letters. And then we have 10 choices, and we're selecting 4 numbers. And the order of them clearly matters because it's a password. You won't necessarily always see the words order is important, order is not important. Sometimes you have to make the judgment for yourself. We haven't seen the order not important questions yet, but just keep it in mind as we keep going. So 26, you're picking 3, 10, you're picking 4 for the digits. We can get each one independently and then multiply them together, or you can type it in all at once. Probability, PR3. So we get 15,600 ways we can choose a letter. This is just the work. You don't necessarily need to have shown this. And then times 5,040 ways you could choose a digit, the numbers, or the 4 numbers. Multiply those 2 things together. Delete. Yes, and we get the same thing. So you can think through it either way. My preference is counting principle, but it's really up to you. Okay, next example. How many distinct ways are there to write the letters in the name Mahayana, a type of Buddhism, and in the name Michelle? So this one is going to use the last of the 3 that we saw because we're using them all, but we've got repetition amongst them. So let's start with Mahayana. We have 1, 2, 3, 4, 5, 6, 7, 8 total letters. So it'll be 8 factorial divided by, and then divide out the repetition. We have repetition amongst the A's. There are 4 of them, so that's going to be our and 1. Do we have repetition anywhere else? Nope, that looks like it. So all we have to divide out is a 4 factorial. 8 factorial over 4 factorial. You can do it in the calculator, do it by hand. We're going to get 1,680. Comparatively, in the name Michelle, these are 2 separate questions. Again, we have 1, 2, 3, 4, 5, 6, 7, 8 choices or letters. And then where do we have repetition? Here we have repetition amongst the E's. There are 2 of them, so that's our N1. And amongst the L's, 2 of them, that's our N2. So divide out a 2 factorial and a 2 factorial. In this case, we get 10,080. You can do this work by hand or type each piece in the calculator and then divide. But I just want to show you the comparison. This is how you would do each problem. You can see in both cases we have a word that is 8 letters long, but it just depends how much repetition and where it falls on what your final outcome would be. There's no quick, simple way to do this at once. You just have to make the full analysis. Comparatively, something like the password, maybe you can use the formula a little bit more, or you can go with counting principle. It's up to you. All right, so let's do some practice problems. You've got 3 here. Go ahead, pause the video, go through these. We will see if we're on the same page in a moment. Okay, so the first problem, an Israeli handball tournament has 7 players on a team. The 4 players who score the most goals will be listed in the order of who scored the most to least on the scoreboard. How many different ways are there for the names to be listed? Well, we definitely know that order is important because this line right here, it's saying they're going to be listed from who scored most to least, and it's the top 4 listed in their order. So how many different ways can they be listed? If you use the counting principle, you would say we're placing 4 people. There are 7 players in the team, so 7 different people could be there first. 6 could be second. 5 could be in the 3rd spot, and then there'd be 4 choices for the last spot, which would give you 840. Alternatively, you could use the formula and say there are 7 players, and I care about the order of 4 of them. So 7p4, type it in the calculator, and you would get 840. Same answer either way. Again, you only need to do it one way. Pick one, you can stick with it, or you can go with whatever feels right per problem. All right, the second one, you need a 6-digit extension, your options 0 through 9. The first 3 must be odd with no repetition, and the last 3 can be anything. And a special note, 0 is not odd. So for this one, because the first part has no repetition, so you could use permutation there, but the last 3 can be anything, you're kind of stuck with counting principle there. So we're making 6 choices. The first 3 have to be odd with no repetition. So how many choices are there for each of these? Let's list the digits. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. They have to be odd, so it can only be 1, 3, 5, 7, or 9. So in the first choice, we need an odd digit. We have 5 choices. There's no repetition. So how many choices do we have on the second selection of digit? It's common for people to say 3 because you want to believe that it should be another odd number sitting there, but that's not the case. We had 5 choices. One of those 5 is gone, whichever one we don't know. There are only 4 choices now of odd digit. Maybe 7's the one that's gone. So 1, 3, 5, or 9 are your choices. Maybe 1's the one that's gone. 3, 5, 7, 9, you have 4 choices on your second selection. The third selection, then 2 of them are gone, so there's only 3 left. And then the last 3 can be anything. Anything. Repetition's fine, anything. So then you have 10 choices, 10 choices, 10 choices. Because it doesn't matter about repetition, they can be anything. So multiply these together, 5 times 4 times 3, 10, 10, 10, gives us 60,000 different ways. It's a 0. 60,000 different ways you could choose that 6-digit extension. Okay, and then the last question, how many different ways are there to write the letters in the word Wissen, which is the German word for knowledge? We have 1, 2, 3, 4, 5, 6 different choices. So 6 factorial divided by, we're using them all, but we have repetition amongst them. There's repetition amongst the s's. There are 2 of them. So take out or divide out a 2 factorial. 6 factorial down the line is 6, 5, 4, 3, 2, 1. 2 factorial is 2 times 1. 2 times 1 cancel. 6, 5, 4, 3. You can't always do it like, you can always write it out like this and do it by hand, but it doesn't always just end up being the first few. It's a little bit more complicated, so just go through the whole process. 6, 5, 4, 3 gives us 360. Make sure it's right. Yes, 360. So 360 different ways you could rearrange the letters in the word Wisen and get a different variation on the letters being there. Okay, so this video was about the counting principle and permutations. We saw a lot of problems where you had the option of doing counting principle or permutation, and that'll pretty much be the case moving forward. But I want you to definitely be comfortable using the formula, because when we move to the next video, that's really going to be your only option. I'll explain how the formula works, but it's a bit more complex. You'll prefer the formula. All right, so I'll see you soon for another video.